Hi guys, my name is Chris. Welcome back to our dokak.net tutorial. Today we're going to learn about how to make this awesome pyro effects in Houdini. And as you can see here, we've got three big elements. The first one is the giant smoke exploding in the center. And then there are a lot of thin smoke trails on the side. And finally we've got some ground smoke at the bottom as well. So let's learn how to make this. Let's get started. So first of all, please open your Houdini, and I'm gonna teach you in Houdini 18 today. And I would like to make my network view a little large like this. And let's make a geometry first. And if you hit the C on the keyboard, and the color palette will pop up like this, I'm gonna change this node to red, and I'm gonna name this fx underscore. And if you hit the P on the keyboard, the parameter view will pop up like this as well. And let's make some space, and let's dive inside this node. And we're gonna need a source. So I started with a sphere. And let's make this primitive tied to polygons so we see some points and primitives. Also, let's change this frequency a little bit large number so we see more points and primitives. And then what I'm gonna do is I'm gonna set the initial velocity from here. So let's make a attribute blob and connect this, and I'm gonna name this initial velocity. So let me explain what I'm gonna do in this flop, and then we'll come back. So we've got a sphere like this, and sphere has a lot of points onto this, right? And each point has normal direction. It has normal, right? Like normal direction, each points. And we're gonna use this normal as our initial velocity. This is gonna be just velocity. So if we do the particle simulation from this, the particle will be spread out. It's moving from, here to there. Like the particle will be, fly away. So that's why we want to use normal direction. So let me show you. So dive inside your VOP, and I'm gonna, as I told you earlier, I'm gonna connect this normal to our velocity. But then we can visualize this. If you hit this button, you see nothing. But if you go inside the sphere, we see some trails. This is the velocity, the initial velocity. And let me just change this connection like n to n, and then we visualize this normal direction as well. Then we can really easily see where it's pointing out. So are they different? The velocity, when I change this to v and n, are they different direction? No, they're exactly same vectors. Just the display is different. So let me explain this here. So I need to explain you first of all what a vector is. A vector is defined by two elements. The first one is the direction. The direction. So the vector, a vector is just a line, right? But it has direction, so it's pointing like this, for example. And also there's second element, which is the magnitude. The magnitude is just the length of this vector, of this line. So for example, if we imagine this vector is onto 2D space, not 3D space. Of course, the vector is composed by 3 elements, but let's just imagine it's in the 2D space. So there are just the x and y axis, and if there's a vector like this, right? In this case, the x element will be, for example, like 2, and this y direction, y-axis is 1. So this vector can be defined by 2, 1, right? This is x and this is y. And there gotta be a length as well, like this magnitude, right? So please understand that first and come back to here. And there's as I told you earlier, there's a normal direction and there's an arrow because it's direction, right? But when we visualize using the trail, it seems like looking like this, right? Inside the sphere. But are they different? No, they're exactly same. So even though when we visualize the trail, it becomes it appears inside the sphere, they are same because it's pointing like this direction, same direction. So this V and this normal are exactly same thing. It's just a visualization thing. Okay. So I'm gonna just connect this to N for now because it's really easy to see here. And also what I'm gonna do is I would like to apply noise to this vector because these are all same vectors, meaning like they all has same length of vector because it was normal, right? So it's like a normalized length. So everything has one length, 1 meter length. So I would like to break this the same line. So that's why I want to use the noise. So what is noise? In the noise, you know, the noise is just like this periodic, like, you know, graph, right? You might already have seen a lot of these noise or used a lot of noise before. So this is x and this is y. So the noise is just a function. So noise function has some x value and the result will be y. So for example, if the x was 2 here, and it's gonna find the corresponding y value. So for example, this will be like about 1.8, for example. So this can be written like this: noise 2 in the parentheses, and it's gonna result in 1.8, right? So what we're gonna do is we're gonna multiply this noise result onto our normal. Why is that possible? Why is that possible? Yeah, let me explain this first. So I said a vector has magnitude, right? So if you multiply vector by a float number, this is gonna affect your magnitude. So for example, we have 1 meter vector, right? And the arrow like this. And if we multiply this by half, like a 0.5, this will result in the half length. So it's gonna be it's pointing out same direction though, but it's gonna be just half length. You get the idea, right? And if we multiply by 2 on the contrast, like a double, and this vector will be doubled as well. The length will be doubled, so it's gonna be, this vector will be like this, and it's gonna be 2 meter, right? It's easy, right? And that's why we can multiply our normal by this noise result. So let me draw this first. So we've got sphere, and we have each point has normal like this, right? Now they're all same length, 1 meter. But if we multiply this by our normal, the length of each vector will be changed. So for example, this will be maybe getting shorter and shorter, and this one will be larger and a lot larger, like this. So as a result, it's gonna make like this type of noise, right? Not the same direction, not the same length at all. And I'm gonna show you this by make some noise node here. So let me check. Okay, I used there are a lot of noise in this level, like a Vex builder. I used a anti-alias noise here, and let's connect to P2 position, and I'm gonna multiply, as I explained, I'm gonna multiply this normal by this AA noise, and then the result will go to N. So here you can see it's weird to see like this black and white image, but this is because just the normal changed by our noise. So let's hit W on the keyboard so we can see the wireframe mode. So this is not really color, this is just normal thing. So let's just see as a wire view, and we see already it's broken down, the same length of normal already broken down. So if you hit the D on the keyboard, it's a shortcut of the display option. And if you go to the guides, and here we have scale normal, and let's make it just 1, so we see more like a longer normal vectors. Okay, it's easier to see, right? And now you can see it's a very there is variation on the normal length. And because this AA noise result in the value from minus 0.5 to positive 0.5, the direction also changed in some places, like the opposite direction. So some goes inside and some goes outside of the sphere, because we multiply this. And so in order to see this, what it's gonna do, we have to, let's make a pop network and connect this to the first input, and then dive inside this pop net and just I'm gonna just hit the play button. So of course we have to change this normal to our velocity, right? Because in this popnet, this pop source has this attribute tab, and there's a parameter called inherit attributes and also initial velocity, and it only understands the attribute called v here, right? And play again, and there is some changes, right? And as I explained you, and some particle goes inside and some particles go outside because of the initial velocity we set. And this is very cool, right? And let's change the display setting a little bit. Hit the D again and go to background tab and change this color scheme to dark so we see more clearly, right? This is very cool. So now that we already set the initial velocity, we just give some small changes here. So let's dive inside this bob again, and I change this frequency to double, like 222. So the frequency in the noise, what it's doing is, let me explain by drawing. So it's a very simple theory. Frequency in the noise, just to make it more frequent or less frequent of the noise pattern. So for example, the noise, we have this noise, right? And if you increase this frequency by double, and it's gonna be more frequent. That means it's gonna make this, let me just draw this arrow axis, like X and Y. And it was a 0 to 1 before, right? To start with from here to end here. But if you multiply the frequency by 2, it's gonna make shorter. That means the graph will be changed like this. So it's gonna be about half over here. So same pattern but different period, right? And if you multiply by half on the contrast, it's gonna be more smoother graph. Let me draw this like this. So in order to finish this pattern, it's gonna be doubled. So this will be 2 on the x-axis. So it's just, different frequency. So if you've got higher frequency, it's gonna make a lot of, I cannot draw this well, but it's gonna make a lot of frequency. And if you decrease the frequency, it's gonna make more like smoother, smoother frequency. Yeah. Okay, so that's why I increased a little bit, like a double. So 222 here. And also the amplitude. If you want to visualize, because it's connected to V, so let's turn on this button, and we cannot really see well, but it's very short. So let's increase this amplitude of the noise like 100, and we finally see so much clearer, right? And then as we increase the amplitude, it's gonna affect our simulation. And let's play it again, and now you see it's exploding really fast, and it makes a lot of this different nice pattern right here, right? And if we were not if we were not using the noise, it won't make this nice pattern. It's gonna just a giant ball exploding. And before we do before we do further, let's go dive inside this VOB again. On top of this initial velocity, I added another vector. So let's make add and connect here, and the middle mouse button and promote parameter, and then click this parameter and name it like a direction or whatever you want to name it. So I named it like a direction. And the important thing is we have to change this type to a vector, 3 floats vector, and go upper level, and we see like there is a direction parameter here, and let's visualize this direction again, and let's change this direction Y. So I set it to 100. So what it does is it's just adding this direction vector to our noise vector. So there is still, noise affecting, there is still this noise affecting our initial velocity, but we've also got another direction, so it mostly goes upward, right? And then I changed this noise amplitude again, 500. So you see it's still like a noise, but there's also like a direction vector, so it's gonna go upward like this. So you get the idea, right? Like it's going, forever, because there's no gravity or other external force. So let's change onto our network here in the PopNet. So first of all, let me change some gravity. Let's add gravity force and then connect to here. Okay, and play it. And is there any change? Yes, there is change, because of the powerful initial velocity, it's gonna exploding in the beginning, but then it's gonna go downwards, eventually, because we have a gravity here. But when I play this play blast, I forgot to turn on this real-time toggle, so let's check this real-time toggle, because we want to just to see 24 frames per 1 second. So this is gonna be real-time, right? It's very slow, right? It's really amazing like how slow it is. So it's just, this is not what we want. This is too slow. So what's wrong? And also these particles will be our source. We don't want to make it, release particles forever like this. We just want make some particles in the beginning, and then we want it to stop it, right? We want to stop it. So it's very simple. In the pop source, we just go to birth tab, and in the constant activation, we just put some expression here, like conditional expression. So only if the $f is our current frame number, so only if the frame number is less than 10, so it's gonna make particles until frame 10, and then it'll stop emitting particles. You see, right? And also we're gonna increase this constant birth rate. This is just the meaning it'll make 5,000 particles per frame. So 5,000 particles during 24 frames, right? Because 24 frames is just 1 second. So we're gonna increase this to 200,000 like this. So it's gonna make more particles. like this. But then we need to, because imagine if this grid is our ground, we don't need these particles under the grid, right? So we can just kill some particles with that go in under the 0. So let's make a pop kill node and just connect it. And if we turn on this enable button, and the vex will be running, so this dat equal 1 will affect our particle sim, so it won't make any particles anymore. And on the other hand, if the dat equals 0, it's gonna make particles, right? So we just we want to put some expression, like conditional expression. So if the particles, the position in terms of y direction, if it goes under the ground level, we want to make it that. So let's play again. And if you see, if the particle go under the 0, it'll be deleted. So it's cool. So it's very funny, I also made a ground plane, and then merge, and left input is ground plane, right input is the particle, and then reconnect like node like this. And if you hit the L on the keyboard, it's gonna rearrange your network view really clean. Yeah, I didn't have to use this pop kill or like either of these two nodes because I don't know why I did this, but I just want to keep it consistent from my previous setup. So yeah, let's play it again. If we play, and it's not gonna go inside, under the 0 ground, right? Because we have a ground plane. So I don't know why I made this pop kill. And then here, yeah, if you see here, this the number is the scene scale, right? Because I imagined like this, the explosion happening within like for example like 50 meters, not that like a giant space. But if you see our simulation here, it's reaching out until like about 1,000 meters, and this is too huge, and I don't want to make it too huge value. I want to make it kind of a realistic. If you imagine like this explosion, it's gonna only like maximum like 100 meters, not that crazy. So I want to make it really for example, like I want to make the explosion happening until here, but we have two giant explosion here, so that's why it seems really slow explosion, right? So let's make it. But if we zoom inside, and if we imagine the explosion will happening until here and play it, and it's really fast, fast explosion. We just need to stop it somewhere, and we can do that by adding pop drag node. And pop drag node will make the particles slow down over time like this. Let's hide this ground plane, and let's play it again. And you see, it's not gonna reach out until like 1,000 meters again, but it's too strong. The drag force is too strong, and this air resistance is too much, so I decreased as 0.2, and let's see what it happened. And now it's much better. So play, and it goes until like 25 meters, so total like left and right side, total is about 15 meters, which is happening right here. Also, if you see close up, there's like a collision onto the ground plane, and they're like bouncing, right? I don't want to bounce too much, so let's make our physical, go to physical tab on the pop object and make it the bounce just to 0, so it won't bounce up that much, it just stays there. So the particle, the source sim is done. So let's go upside, and let's change this name a little bit. I named this dot network as explosion source sim, and in order to pull the result of our simulation, we need to make this clear. We need to put down a specific name here. So because the object has this star sign, it brings everything in the sim, so like a ground and particles, but what we need is just pulling the particles movement. So go inside, and this pop object has, if you go to here, you see object name, and it has a $OS, which is the node's name. So if you middle mouse button here, you see what it exactly means. So I'm gonna just copy this parameter, and go to here and right click and paste relative references. So if you middle mouse here again, it's just pulling the pop object's result, simulation result. And yeah, cool. And we want to make this particle, we want to convert this particle to a volume, and then do the smoke simulation from there. But then on the frame 1, it already pops up, right? We already have particles here, and we don't want that. We just want to there's nothing on the frame 1, and then the explosion appears. So I added a just transform. I mean, you can do whatever you want. You can do that. You can achieve that inside this dot network, but I prefer to just do that not inside the dot network, and just using just a simple node here like this. So in this node, you can just adjust this uniform scale, and like this, and then I put some expression here. Okay, let me check. I put expression like this. So I used the fit expression and $FF, and these 1, 3 becomes 0 to 1. And if you play this, so there's nothing on frame 1, and then from 2 it's exploding, right? So what it does, what the fit expression does is it's just remapping the old values. So here, if I explain this by drawing, oops. Okay. So this fit expression is very important and very useful. So you guys have to understand this very well. So this fit expression has 5 elements inside this parenthesis. So fit and A, B, C, D, E, 5 element, and it's gonna result in something, right? And first of all, this A means just a value, what you wanna remap. So this is gonna be just a value, what you wanna make changes. And this B and C is old values, and this D and E is a new value. So in A, I put $FF, right? $F is just the floating type of the $F, which is frame number, current frame number. And then in old value, I put 1 and 3. And in new value, I put 0 to 1. So what, if I explain this again, so when this frame number change from 1 to 3, please remap those value to 0 to 1. So if the frame number goes more than 3, like 4 and 5, 6, if we play the play blast, it's gonna be increased, right? And it's gonna remap to 1, no matter how it no matter how big it's gonna be. And if the $F under the 1, it's gonna just remapping to 1. So oops, so let me draw this. And so if this axis is means $F, if we play the $F, from here we always start with frame 1. So frame 1 and frame 2, like this, right? And because of this fit expression, we'll get here on frame 1, we'll get, because of this new value, we'll get 0, and on frame 3 we'll get 1 because of this new value. And if the frame number is more than 3, it's just gonna go same like 1, value 1, right? And if the frame number were under 1, like a 0 or -1, it'll be just a 0, like a clamped, right? And if the frame number is a 2, by the way, it's gonna just because of this is the in between on frame 1 and 3, so it's gonna make about 0.5, right? So it's just basically remapping of the value. So it's very useful. So that's why we get this on frame 1 we get 0, the uniform scale 0, so we see nothing. But then if we go to 2, we see the uniform scale change to 0.5, and on frame 3 we see uniform scale 1. But from then we see just scale uniform scale just 1, same 1, right? Same thing. So it's not gonna be different from our original sim after frame 3. So see, okay, cool. But then I modified this expression a little bit further. What I did was just I used power module power function again. In the second input I put 0.5, and you don't see really much difference, but you see more exploding in the beginning. So what it does is the power function does is, this is very important too. So because the fit function result in 0 to 1 value, this 0 to 1 is just constant. So which means on the graph, if this were like x and y axis, and 0 to 1 is just a constant graph like this. So when the x is 1, it becomes y value 1. But when we power this graph, and when we power this graph by 2, what it's gonna make is it's gonna make like a banded, like this band graph, you know. And on the other hand, if I do like power x by like less than 1, which is like 0.5, it's gonna make this graph. Okay, so what it does is more, if it were in the same axis, in the same x position, like here is like a 0.2, for example. The original graph indicated what, 0.2, right? But when we modify this graph by power this, it's gonna make a lot higher value, which is about 0.7 or something like that. So what it does is it's making more powerful in the beginning, right? So that's why it's gonna make more powerful. Of course, after frame 3, it's gonna make exactly same as this original simulation, so it won't affect after that. And now that we artificially changed our simulation in the beginning, like using transform, we need to recompute the velocity. And so make a trail node, and then just the result type to compute velocity. So we have, so you see like the messed up velocity, because we didn't turn on this match by attribute by ID. Because the particle simulation, we have an ID attribute, and just for safety we have to turn it on, so it calculates correct velocity. So I'm gonna name this just compute V, and we're gonna do the smoke simulation using these particles. But before that, we need some attribute set. So let's make a attribute wrangle and name it as just this. We're gonna set some attributes, so set attributes. And here what I'm gonna do is just do some vex expression, which is let me explain later on a little bit, but I want to make a variable called f1, which is float type, and I'm gonna use fit expression again, and the value will be the ag attribute, and the old value will be 0 to 1 become 1 to 0, so inverted. And I'm gonna set this f1 to a alpha attribute like this. So as soon as I change the alpha attribute or added alpha attribute, the display becomes changed and it disappears, right? But it really disappeared? No, there are still points. It's just becomes 0 alpha, so that's why we don't see anything later on. So we, like we use the fit expression here. This fit expression is exactly same thing. We just used our age attribute. So what is age attribute? The age attribute is coming from this simulation result. This here has very useful age and ID and also velocity attributes, and among these attributes we just used a age attribute. So what is the age attribute? Let me explain here. So the age attribute is very simple thing. So when the particle is born, gets born in the first frame like this, it has the age 0, and it's over time it's aging, literally. So after 2 seconds, you know, it's like a moving like this direction, right? So after 2 seconds, the age attribute of this particle, same particle, will be 2. So it's not frame, it's a second, you know. So and every particle has this age attribute. So that means because we use this age in the fit value, so fit and age, if the particle age changes from 0 to 1, it becomes, the result will be 1 to 0, right? So this particle, if this were like the result is y, this particle y value will be 1 because it started from age 0, right? Because this is old value, it'll remapping to 1. So it'll start with 1 y, and then after 1 second, because this is old maximum value, becomes 0. After 1 second, so the particle will travel around here. After 1 second, the y will be 0 because this the new value is 0. Okay, so that's why. And then we assign this value to alpha, and alpha is the attribute that Houdini already understands, and it'll affects our display. So here, really simple Vex grammar, and you get the idea, right? So every particle, whenever they gets born and when they reach age 1, the alpha of their particles, the alpha will change it to from 1 to 0. So that's why when it begins, it's really clear, and then it fades away, right? And also in this attribute wrangle, we're gonna set this f1 value to another attribute, like for example, we're gonna apply this to p scale as well, and also we're gonna multiply this f1 value by this the original velocity of the particle. So like this. Let me explain this later in a bit, but just please write down like this, and then let's move on to next step, which is we're gonna do smoke simulation finally. But before do that, we need to convert this to volume first. So we're gonna have a volume source. So in order to do that, we just make a VDB from particle node and connect this, and we already see here, right? And well, let's make this minimum radius just 0, otherwise it's gonna make error. And then so eventually we have to make this not surface. We need density fog volume like this. So let's turn on this, let's bypass this node and on and off, like what it'll change, you know. When we bypass this node, you know, it definitely affects how this VDB volume does. So what it does is this, we set the p scale here, right? And it affects to our VDB volume. So that is exactly same thing happen when we copy some object onto points. So this is what happens. So when we copy this sphere onto this point, you know, and if we don't have the p scale attribute, and it's gonna make all the same sized spheres, like a radius 1 sphere. But because of that p-scale attribute, we can vary the size, and the p-scale is we set it to f1, and f1 is like a changing value, like 1 to 0, like here, right? So that's why it's gonna be much bigger in the beginning, like the alpha, right? And then over time it's gonna be really small and 0. But of course there is spheres still here, but the size is 0, so we don't see anything. And here in the VDB, so that's why because we have p-scale here, we have a nice varied smoke size here. And let's change this point radius scale here. This is just a global multiplier, so let's make it a little smaller, like this. And then we're gonna so, and here is a voxel size. Voxel size a little bit low here, so that's why it becomes slow. So let's increase a little bit, like a double, and also name it this as a source volume. And if we middle mouse click here, we see like a density volume, density VDB volume created. And but in the smoke simulation, we will also need the velocity smoke. So in the point attribute parameter, just the +1, hit the plus, and this attribute change to, because we have V attribute on the particles, and so select V and name it as V volume as well, and change the vector type to this displacement velocity. And then middle mouse click again, and this time it'll make 2 volumes, which is density and V. And if you in the scene view, just ignore this display thing, because of this V is a vector. Here you see vector. Because of that, it's gonna mess up our display. But if you want to see just the density, you can always just make this split sub or whatever, and just just view just density volume like this. So don't get panic about this display. And just the important thing is we've got 2 volumes here, and now we're ready to do pyro simulation. So one more thing I need to explain you is in this set attribute wrangle, this last sentence is very important as well. So if we see the particle again and display this trail, and if I do this, we multiply. It's not just equal. We have this, star sign equal. This is the same as V attribute equal the existing V multiply by F1. This is same thing. This first sentence and second sentence are the same thing. You just do whatever you want. I'm just gonna bypass this line again. So this is same thing. So we already have this velocity from here, right? From the simulation we have velocity. But then we multiply it by F1 value, which is this value, right? So that's why if we apply this attribute wrangle, the length of the V velocity will be shorter and shorter, and the length will be 0 eventually. So I wanted to make it really, you know, high in the beginning, and then over time it becomes, the length of the velocity becomes 0 as well. So that's why I put this, the last sentence here. Okay, so that's a very important thing as well. Yeah, you might think right now I am explaining you very slow or whatever, but these are really important steps for beginners, and that's why I really explained you by these awesome drawings. But you know, from now on, I'm gonna, you know, later on when we make some like trails and ground smoke, I'm not gonna explain you about these steps that much, so we can, you know, boost our tutorial time. So don't worry about it, and these are really important, and the most important thing is here. And so in the next chapter, I'm gonna talk about how to do our first pyro simulation. See you there.